Hello there, and welcome to Bedtime Science Channel. I am so glad you found your way here. Maybe you've had a long day filled with the ordinary world of everyday physics. Or maybe you are simply curious about the strange and beautiful realm that exists beneath everything we see. Either way, tonight's journey is for you. You have nothing to do but rest. Let your mind relax, your breathing slow, and your thoughts drift like quantum particles through infinite possibility. Because tonight we're exploring quantum physics, the science of the impossibly small, where particles can be in two places at once, where observation changes reality, and where the very foundations of existence follow rules so elegant and mysterious they seem like magic. We'll move gently through this hidden world, from wave-particle duality to quantum entanglement, from uncertainty principles to the strange dance of probability that underlies all matter. Some of what you hear tonight may challenge what you thought you knew about reality. Other discoveries might simply wash over you like gentle waves, soothing and quietly profound. If these calm explorations help you unwind or spark a quiet wonder as you drift towards sleep, consider liking and subscribing to the channel. It helps others find their way here too, one curious soul at a time. Now, let yourself get comfortable. Take a deep breath, and let's begin this peaceful journey into the quantum realm. Quantum physics studies the behavior of matter and energy at the smallest possible scale. These tiny particles follow rules that seem magical compared to our everyday world. In this microscopic realm, particles can exist in multiple places at once, creating a reality more mysterious than any dream. The word quantum comes from the Latin word meaning how much or amount. It represents the smallest possible unit of energy that can be absorbed or released by matter. Think of energy as flowing not like water, but like tiny discrete droplets that cannot be divided further. Quantum mechanics was born in the early 1900s when scientists discovered that energy doesn't flow continuously. Instead, it comes in small packets called quanta, like steps on a staircase rather than a smooth ramp. This discovery revolutionized our understanding of reality itself. Electrons don't orbit atomic nuclei like planets around the sun, as once believed. Instead, they exist in probability clouds called orbitals, where they might be found at any given moment. These clouds represent all the possible locations where an electron could exist simultaneously. The uncertainty principle states that we cannot know both the exact position and momentum of a particle at the same time. The more precisely we measure one property, the less precisely we can know the other. This isn't due to imperfect instruments, but a fundamental property of reality. Quantum tunneling allows particles to pass through barriers that should be impossible to cross. It is like a ball rolling through a solid wall instead of bouncing off it. This strange phenomenon makes many modern technologies possible, including computer processors and medical imaging devices. When particles become quantum entangled, they remain mysteriously connected regardless of distance. Measuring one particle instantly affects its entangled partner, even if they're separated by vast distances. Einstein called this spooky action at a distance. The double-slit experiment reveals that particles can behave like waves when unobserved. Light and electrons create interference patterns when passing through two slits, suggesting they travel through both slits simultaneously. Yet, when we try to observe which slit they use, they behave like particles again. Quantum superposition means particles can exist in multiple states simultaneously until measured. A quantum particle can spin both clockwise and counterclockwise at the same time, existing in all possible states until observation forces it to choose one. This is like a coin that spins heads and tails simultaneously until it lands. Schrödinger's famous thought experiment describes a cat that exists in superposition of being both alive and dead. This paradox illustrates how quantum rules, when applied to larger objects, create seemingly impossible situations. The cat demonstrates the boundary between the quantum world and our everyday experience. Quantum computers use the strange properties of quantum mechanics to process information. Unlike traditional computers that use bits as either 0 or 1, quantum computers use qubits that can be 0, 1, or both simultaneously. This allows them to perform certain calculations exponentially faster, than conventional computers. The quantum Zeno effect occurs when frequent observation prevents a quantum system from evolving. Like a watched pot that never boils, a quantum particle that is constantly measured won't change states. This demonstrates how the act of observation fundamentally affects quantum reality. Virtual particles constantly pop in and out of existence in empty space. These temporary particles appear from the quantum vacuum for incredibly brief moments before disappearing again. Even empty space buzzes with this constant creation and annihilation of virtual matter. Quantum field theory describes particles as excitations in underlying energy fields. What we perceive as a particle is actually a wave, like disturbance in an invisible field that permeates all of space. Every type of particle has its own corresponding field throughout the universe. The many worlds interpretation suggests that every quantum measurement splits reality into multiple universes. Each possible outcome of a quantum event occurs in its own parallel universe. While unproven, this interpretation elegantly explains quantum mechanics without requiring wave function collapse. Quantum decoherence explains why quantum effects disappear in large objects. Interactions with the environment cause quantum superpositions to break down rapidly. This is why we don't see everyday objects in multiple states simultaneously, despite being made of quantum particles. The Pauli exclusion principle states that no two electrons can occupy the same quantum state. This rule is responsible for the structure of atoms and the stability of matter. Without this principle, all electrons would collapse into the lowest energy state, and atoms, as we know them, couldn't exist. Quantum spin is an intrinsic property of particles that has no classical equivalent. Despite its name, quantum spin doesn't involve actual rotation. Instead, it is a fundamental property like electric charge, determining how particles interact with magnetic fields and each other. Zero-point energy is the lowest possible energy that a quantum system can possess. Even at absolute zero temperature, quantum systems retain this minimum energy due to the uncertainty principle. This means that motion never completely stops at the quantum level. Quantum interference can make particles more or less likely to appear in certain locations. When quantum waves overlap, they can add together constructively or cancel each other destructively. This wave-like behavior creates the beautiful patterns we observe in quantum experiments. The measurement problem in quantum mechanics asks how and when wave function collapse occurs. While we know that observation somehow selects a single outcome from multiple possibilities, the exact mechanism remains one of physics' greatest mysteries. Various interpretations attempt to explain this fundamental puzzle. Quantum chromodynamics describes the strong force that binds protons and neutrons together. This theory involves particles called quarks that carry a property called color charge. The mathematics of this field theory helps us understand how atomic nuclei maintain their stability. The quantum vacuum is not truly empty, but filled with fluctuating energy fields. These vacuum fluctuations give rise to measurable effects like the Casimir force between closely spaced metal plates. The vacuum itself participates actively in quantum phenomena. Bell's theorem proves that no physical theory based on local hidden variables can reproduce all the predictions of quantum mechanics. This theorem shows that quantum entanglement involves genuine non-local connections that cannot be explained by classical physics alone. Quantum dots are tiny semiconductor particles that confine electrons in all three dimensions. These artificial atoms have tunable properties that depend on their size, making them useful for applications ranging from medical imaging to high-efficiency solar cells and quantum displays. The quantum Hall effect occurs when electrons in a strong magnetic field form incompressible quantum fluids. This phenomenon reveals exotic states of matter and has led to precise standards for electrical resistance. The fractional quantum Hall effect hints at even stranger physics involving quasi-particles. With fractional charge, Bose-Einstein condensates are ultra, cold states of matter where thousands of atoms behave as a single quantum entity, created at temperatures just billionths of a degree above absolute zero. These condensates allow scientists to directly observe quantum mechanics on a macroscopic scale. Quantum error correction protects fragile quantum information from environmental interference. These sophisticated protocols can detect and correct errors without directly measuring the quantum state itself. Such techniques will be essential for building large-scale quantum computers. The uncertainty principle applies to many pairs of properties beyond position and momentum. Energy and time, angular position, and angular momentum, and electric and magnetic field components all obey similar uncertainty relations. These limitations are built into the fabric of reality. Quantum teleportation can transfer the complete quantum state of a particle to a distant location. While the original particle is destroyed in the process, its exact quantum information appears elsewhere instantaneously. This technique doesn't violate relativity, because classical information must still travel at light speed. Cavity quantum electrodynamics studies how atoms interact with electromagnetic fields in confined spaces. When an atom is placed inside a small cavity, the interaction between matter and light becomes so strong that they form hybrid states called polaritons, leading to new phenomena impossible in free space. Quantum phase transitions occur at absolute zero temperature, driven purely by quantum fluctuations, unlike thermal phase transitions caused by temperature changes. These transitions happen when quantum parameters like magnetic field strength cross critical values, revealing exotic quantum states of matter. The quantum approximate optimization algorithm uses quantum computers to solve combinatorial problems. By encoding optimization problems in quantum circuits, this algorithm can potentially outperform classical methods for certain types of difficult computational challenges. Quantum coherence measures how well a system maintains its quantum properties. Like the clarity of a wave pattern, coherence can be disrupted by interactions with the environment. Preserving coherence is crucial for quantum technologies and helps us understand the transition between quantum and classical behavior. The Aharonov-Bohm effect shows that electromagnetic potentials, not just fields, have physical significance in quantum mechanics. Electrons traveling around a solenoid are affected by the magnetic potential, even in regions where the magnetic field is zero, demonstrating subtle quantum electromagnetic phenomena. Quantum supremacy occurs when quantum computers solve problems impossible for classical computers. This milestone demonstrates the point where quantum devices can perform calculations that would take classical computers impractical amounts of time, marking a new era in computational capability. The Berry phase is a geometric phase that quantum systems acquire when their parameters change slowly. This phase depends only on the path taken through parameter space, not on the speed of travel. Berry phases appear in many quantum phenomena and have applications in quantum computing. Quantum sensors use quantum mechanical effects to achieve unprecedented measurement precision. By exploiting quantum entanglement and superposition, these devices can detect magnetic fields, gravitational waves, and other phenomena with sensitivity approaching fundamental physical limits. Quantum cryptography provides theoretically unbreakable communication security. Any attempt to eavesdrop on quantum encrypted messages necessarily disturbs the quantum states, alerting the communicating parties to the presence of an intruder. This security comes from the fundamental laws of quantum mechanics. The weak measurement technique allows limited information about quantum systems without complete wave function collapse. By making very gentle measurements, scientists can glimpse quantum trajectories and gather information about quantum systems while minimally disturbing their evolution. Quantum metrology uses quantum resources to achieve measurement precision beyond classical limits. By carefully preparing quantum states and using entanglement, quantum sensors can measure physical quantities with accuracy that surpasses any classical measurement technique. The quantum Fisher information quantifies how much information a quantum state contains about an unknown parameter. This mathematical framework helps optimize quantum measurement strategies and determines the ultimate limits on measurement precision that quantum mechanics allows. Quantum walks are the quantum version of random walks, where particles can explore multiple paths simultaneously. These quantum processes show fundamentally different behavior from classical random motion, potentially leading to faster searching algorithms and better understanding of transport phenomena in quantum systems. The quantum delayed choice experiment shows that the past can seemingly be changed retroactively. By choosing how to measure a photon after it has already interacted with a beam splitter, experimenters can determine whether the photon behaved like a wave or particle in the past, challenging our concepts of temporal reality. Quantum simulation uses controllable quantum systems to study other, less accessible quantum phenomena. By creating artificial quantum systems in the laboratory, scientists can explore exotic states of matter, test theoretical predictions, and understand complex quantum many-body systems that are impossible to calculate classically. The quantum speed limit determines the minimum time required for quantum systems to evolve between different states, like a universal speed limit for quantum change. These bounds constrain how quickly quantum information can be processed and how fast quantum gates can operate. Quantum annealing uses quantum fluctuations to find optimal solutions to complex problems. By slowly reducing quantum fluctuations, these systems can escape local minima and discover better solutions than classical optimization methods. This approach shows promise for artificial intelligence and logistics problems. The quantum eraser experiment demonstrates that quantum behavior can be retroactively determined, even after a particle has traveled through a double-slit apparatus, erasing which path information can restore the interference pattern. This suggests that quantum reality might not follow our usual concepts of temporal causations. Squeezed light reduces quantum noise in one property by increasing uncertainty in another. These specially prepared light states can measure distances more precisely than classical light allows, making them essential for detecting gravitational waves and improving atomic clocks. Quantum non-locality means that spatially separated quantum systems can share correlations stronger than any classical physics allows. These correlations appear instantly across any distance, suggesting that the quantum world operates according to principles fundamentally different from our everyday experience. The no-cloning theorem states that it is impossible to create an exact copy of an unknown quantum state. This fundamental limitation protects quantum cryptography and explains why quantum information is fundamentally different from classical information. You cannot perfectly duplicate a quantum state without destroying the original quantum decoherence timescales vary dramatically depending on the system and environment. Some quantum states can maintain coherence for microseconds, while others, specially protected ones, can persist for hours or even days. Understanding and extending these times is crucial for practical quantum technologies. The quantum Cheshire cat effect describes situations where a quantum particle and its properties can be separated. In certain experimental setups, a photon can follow one path while its polarization follows another, like the Cheshire cat's grin remaining after the cat disappears. Quantum biology studies quantum effects in living systems. Some processes in photosynthesis, bird navigation, and enzyme catalysis may rely on quantum coherence and entanglement. This emerging field explores how life might harness quantum mechanics for biological advantage. The quantum pigeonhole principle shows that quantum particles don't always follow classical logic. In the quantum version, you can sometimes put 3 particles in 2 boxes, with none of the boxes containing more than 1 particle, violating our everyday understanding of counting and distribution. Quantum contextuality means that the result of a quantum measurement can depend on which other measurements are performed alongside it. This property, unique to quantum systems, shows that quantum particles don't have definite properties independent of the measurement context. The quantum coin flip can land on both heads and tails simultaneously. Unlike a classical coin that must be either heads or tails, A quantum coin can exist in a superposition of both states until measured. This demonstrates the fundamental difference between quantum and classical probability. Quantum retroaction suggests that future measurements can influence past quantum states. This counterintuitive effect, observed in delayed choice quantum eraser experiments, challenges our understanding of causality and the flow of time in quantum mechanics. The quantum bus effect occurs when multiple quantum systems share the same environment. Information can be transferred between systems that never directly interact, mediated by their common interaction with environmental degrees of freedom. This effect is important for understanding quantum information processing in noisy environments. Quantum radar uses entangled photons to detect objects with enhanced sensitivity. By comparing the quantum correlations between transmitted and received photons, quantum radar can potentially operate more effectively in noisy environments and detect stealth objects better than classical radar. The quantum refrigerator uses quantum effects to cool systems below what is possible with classical thermodynamics. By exploiting quantum coherence and entanglement, these devices can potentially reach lower temperatures and operate more efficiently than conventional cooling methods. Quantum batteries could store energy in quantum systems rather than classical ones. These theoretical devices might charge faster and store energy more efficiently by exploiting quantum effects, like superposition and entanglement. Research suggests they could outperform classical batteries in certain applications. The quantum compass uses quantum entanglement instead of magnetic fields for navigation. By measuring quantum correlations in specially prepared atomic systems, such devices could potentially provide navigation information without relying on GPS satellites or magnetic compasses. Quantum communication protocols allow secure transmission of information over long distances. These methods use quantum properties like entanglement and superposition to detect eavesdropping and ensure message integrity. Quantum internet networks could revolutionize global communications. The quantum heat engine operates using quantum working fluids instead of classical gases. These engines can potentially exceed classical efficiency limits by exploiting quantum effects like coherence and squeezing. They represent a new frontier in quantum thermodynamics. Quantum machine learning combines quantum computing with artificial intelligence algorithms. By processing information in quantum superposition, these systems might solve certain pattern recognition and optimization problems exponentially faster than classical computers. The quantum gyroscope uses quantum effects to measure rotation with extreme precision. Instead of mechanical spinning masses, these devices use quantum properties of atoms or photons to detect angular motion, potentially offering superior accuracy for navigation and scientific instruments. Quantum chemistry simulates molecular behavior using quantum computers because molecules are inherently quantum systems. Quantum computers might naturally solve chemistry problems that overwhelm classical computers, potentially revolutionizing drug discovery and materials science. The quantum clock exploits quantum superposition to measure time with unprecedented accuracy. By using quantum states of atoms or ions, these clocks can potentially outperform current atomic clocks and test fundamental physics theories about the nature of time itself. Quantum algorithms for optimization could solve complex scheduling and routing problems. These quantum approaches might find better solutions faster than classical methods for problems like traffic flow optimization, financial portfolio management, and supply chain logistics. The quantum memory stores quantum information for extended periods while maintaining quantum properties. Unlike classical memory that stores definite bit values, quantum memory preserves superposition and entanglement, essential for quantum computing and communication networks. Quantum error rates in current systems are still too high for most practical applications. Building fault-tolerant quantum computers requires reducing error rates by orders of magnitude while scaling up the number of qubits. This remains one of the greatest challenges in quantum technology. The quantum advantage occurs when quantum algorithms outperform the best-known classical algorithms for specific problems. While full quantum computers remain under development, researchers continue discovering new quantum algorithms that could provide significant speed-ups for important computational tasks. Quantum Foundations research explores the philosophical implications of quantum mechanics. Questions about the nature of reality, measurement, consciousness, and information continue to drive fundamental research into what quantum mechanics tells us about the universe. Quantum entanglement networks could connect quantum computers across the globe. These quantum internet systems would enable distributed quantum computing, ultra-secure communications, and new forms of quantum collaboration impossible with classical networks. The measurement problem remains unresolved despite decades of research. Scientists continue debating when and how the quantum wave function collapses, whether multiple worlds exist, or if consciousness plays a role in quantum mechanics. These deep questions touch the very nature of reality. Quantum decoherence occurs faster in warm, noisy environments. This is why quantum effects are usually observed only in carefully controlled laboratory conditions at extremely low temperatures. Understanding and controlling decoherence is essential for practical quantum technologies. The quantum world influences our everyday experience in subtle but profound ways. The stability of atoms, the behavior of electronics, and even the light from the sun all depend on quantum mechanical principles. Without quantum physics, the universe as we know it couldn't exist. Quantum tunneling in biological systems might explain how enzymes work so efficiently. Some researchers propose that quantum effects help biological molecules navigate energy landscapes more effectively than classical physics would predict, potentially contributing to life's remarkable efficiency. The uncertainty principle ensures that the vacuum of space is never truly empty. Quantum fluctuations continuously create and destroy virtual particle pairs, giving the vacuum a rich underlying structure. This quantum foe might hold clues to unifying quantum mechanics with gravity. Quantum entanglement might extend across cosmic distances. Some theories suggest that particles created in the early universe could remain entangled today, potentially providing a quantum connection across the entire cosmos. This cosmic entanglement could influence the structure and evolution of the universe. The double-slit experiment continues to reveal new mysteries about quantum behavior. Modern versions, using increasingly sophisticated detection methods, still surprise researchers and demonstrate that our understanding of quantum mechanics remains incomplete. Quantum thermodynamics studies how quantum effects modify the laws of heat and work. At microscopic scales, quantum coherence and entanglement can change how energy flows and transforms, potentially leading to more efficient quantum engines and refrigerators. The quantum Zeno effect has practical applications in preserving quantum states. By carefully timing measurements, researchers can freeze quantum evolution and protect fragile quantum information from decoherence, extending the lifetime of quantum memories and qubits. Quantum interferometry uses quantum superposition to make incredibly precise measurements. These techniques can detect gravitational waves, measure tiny distances, and probe fundamental physics with sensitivity limited only by quantum mechanics itself. The concept of quantum information has revolutionized our understanding of computation and communication. Information encoded in quantum states can be processed and transmitted in ways impossible with classical systems, opening new possibilities for technology and fundamental science. Quantum field fluctuations might explain the origin of cosmic structure. Tiny quantum fluctuations in the early universe, stretched to cosmic scales during inflation, may have provided the seeds from which galaxies, stars, and planets eventually formed. The many-body problem in quantum mechanics remains largely unsolved. When many quantum particles interact, the complexity grows exponentially, making exact calculations impossible, even for modest numbers of particles. This challenge drives the development of new theoretical and computational methods. Quantum phase transitions can occur without any change in temperature. Driven purely by quantum fluctuations, these transitions reveal new states of matter with exotic properties. Understanding these quantum critical points could lead to novel materials and technologies. The quantum world operates according to probability rather than certainty. Unlike classical physics, which predicts exact outcomes, quantum mechanics only gives us the probability of different results. This fundamental randomness appears to be a basic feature of reality. Quantum mechanics suggests that reality might be fundamentally observer-dependent. The act of measurement seems to play a crucial role in determining physical outcomes, raising profound questions about the relationship between consciousness, observation, and physical reality. The scales at which quantum effects dominate are incredibly small. For most everyday objects, quantum uncertainty and superposition are negligible compared to thermal fluctuations and classical noise. This is why we don't notice quantum behavior in our ordinary experience. Quantum computing faces significant technical challenges before reaching its full potential. Current quantum computers are limited by decoherence, noise, and the need for extreme operating conditions. Overcoming these obstacles requires advances in materials, control systems, and error correction. The interpretation of quantum mechanics remains an active area of debate. Different interpretations, from many worlds to consciousness-based theories, offer various explanations for quantum phenomena. No experimental test has yet definitively favored one interpretation over others. Quantum entanglement has been verified over increasingly large distances. Researchers have demonstrated quantum correlations between particles separated by hundreds of kilometers using both fiber optic cables and satellite links. These experiments confirm quantum non-locality on macroscopic scales. The quantum measurement process itself can be studied using quantum mechanics. By treating measurement devices as quantum systems, researchers are beginning to understand how classical measurement outcomes emerge from quantum interactions. Quantum superposition exists on a spectrum rather than being simply on or off. Real quantum systems can have varying degrees of superposition depending on their interaction with the environment and the precision of measurement. This subtlety is crucial for practical quantum technologies. The boundary between quantum and classical behavior is not sharp but gradual. As systems become larger and more complex, quantum effects typically fade due to decoherence, but the transition occurs smoothly rather than abruptly. Quantum mechanics has led to revolutionary technologies, even though we don't fully understand its foundations. Lasers, transistors, magnetic resonance imaging, and many other modern technologies rely on quantum principles, demonstrating that practical applications can emerge even from mysterious science. The future of quantum technology promises transformative applications across many fields. From cryptography and computing to sensing and simulation, quantum effects could revolutionize how we process information, understand nature, and interact with the physical world. And now, as these quantum mysteries settle gently around your thoughts, let yourself drift deeper into rest. We've journeyed through a realm where the impossible becomes possible, where particles dance in probability clouds and reality responds to observation. In this strange and beautiful quantum world, nothing is quite what it seems. You've wandered through superposition and entanglement, through uncertainty and measurement, through the endless mystery of how the smallest things shape everything we know. These quantum phenomena don't just exist in laboratories or equations. They're here right now, in every atom of your body, in every breath you take. The electrons flowing through your neurons as you dream, the bonds holding your cells together, the very stability of the matter that makes you who you are. All of it dancing to quantum rules, all of it connected in ways we're only beginning to understand. Tonight, as you rest, remember that you are not separate from this quantum realm. You are part of it, made of it, sustained by its strange and wonderful laws. In every quantum interaction happening in your body right now, the universe is writing itself, moment by moment, probability by probability. So let your mind settle into the uncertainty, the beauty, the infinite possibility that quantum mechanics reveals. Let yourself become like a quantum particle, existing peacefully in all possible states of rest, drifting gently through the night. If you happen to still be awake, you can continue exploring the mysteries of science. And if these quiet quantum wonders have helped you unwind, consider subscribing to journey further into the peaceful side of science, one sleepy discovery at a time. Good night, and dream quantum dreams.